So next, I would like to introduce Dr. Jieping Ye. Unfortunately, Dr. Ye cannot join us in person today, so he will deliver his talk online. Dr. Ye is a vice president of Alibaba Group. He was a professor of University of Michigan, Ann Arbor. His research interests include big data, machine learning, artificial intelligence with applications in transportation, smart city, housing, and biomedicine. He won the NSF Career Award in 2010. His paper has been selected for Outstanding Paper Award in ICML International Conference for Machine Learning in 2004, the KDD Best Research Paper runner-up in 2013, and the KDD Best Student Paper Award in 2014. He has also won the first place in 2019, the Inform's Daniel Wenger Prize, one of the top award in operations research practice. Dr. Ye was elevated to IEEE Fellow in 2009 and named as ACM Distinguished Member in 2020 for his contribution to the methodology and application of machine learning and also data mining. Dr. Ye.
Thanks, Henry, and thanks for having me. And good morning, everyone. I'm really excited to be here. And sorry I was not able to join in person this time due to a conflict. So in this talk, I will give an overview of recent history of large-scale models and how they can make an impact in transportation. So over the course of a decade, since 2012 until 2023, the field of AI has witnessed several pivotal milestones that have shaped its impact on society. For example, AlexNet revolutionized the field of computer vision in 2012. Then since Transformer was introduced in 2017, we stepped into the area of large-scale models. And these models, with their unparalleled capacity to process and synthesize vast amounts of information, have fundamentally altered the way we approach very complex tasks. And most recently, OpenAI developed ChatGPT and GPT-4, which transformed the field of NLP and many other areas. So GPT models represent not just the technological breakthrough, but also a societal inflection point, pushing the boundaries of AI integration into everyday life, and igniting also discussions about its potential impact on various aspects of society. So here, the transformer architecture introduced in the paper shown next, this bottom left, right? Attention is all you need, marked a significant milestone in the field of NLP and also AI more broadly. And here, the key features of this architecture includes an innovative attention mechanism and also parallelizable training. So this led to a dramatic reduction in training time and made this model feasible to train large-scale models on a huge amount of data and also improve performance. So the transformers demonstrated SOTA results on various NLP tasks. So the transformer architecture has not only transformed NLP but has also catalyzed innovations across multiple domains of AI, solidifying its position as one of the most influential results of developments in modern AI. So its ability to adapt, scale, integrate with the diverse modalities, not only just text, continue to push the boundary of AI, what is possible in AI research and applications. Since the Transformer introduced in 2017, so many large-scale language models have been developed. We can categorize into three categories. The right side shows these GPT series, which are decode-only models. Then the left side, these are BERT models, BERT series, which are encode-only models. And in the middle, we have this mixture, encoder-decoder models. And then nowadays, we all know this GPT series from OpenAI dominate, has become the mainstream in the field of AI. So let's take a close look at the GPT models. Here you use the example from GPT-3. So GPT-3 as an advanced language model is structurally a transformer-based neural network. Its core function, it's very simple. It's basically try to predict the next word in a text sequence, a task that belies the model's profound capabilities. And here with the training data set of 45 terabytes, it's a huge amount of data. Then GPT-3 simulates an extensive range of linguistic patterns and contexts. And here show the history of these GPT models. So the first model, GPT-1, was released in 2018 with a model size of 112 million. And at that time, a model of 112 million is already a huge model. Right? And then GPT-2 was released just in 1 year. Then the model size is already 1.5 billion. Again, that was a huge model, right? Back in 2019. Then GPT-3 was released just in 1 year in 2020, then with a model size of 175 billion. So you can see in just a few years, the size of the model has increased more than 1,000 times fold. Then last year, 2023, we have this GPT-4. It's used to mixture models, and it's much larger than GPT-3. And the training of GPT has 3 stages. First one is pre-training. Then we have instruction fine-tuning, and then human alignment. So in the first stage, we feed the model with a huge amount of unlabeled text. In GPT-3, we mentioned the 45 terabytes of data. Then in the second stage, we collect a large amount of these QA pairs, instructions, and fine-tune the model using these QA instructions, these pairs. And in the last stage, we align the model with human feedback. In the high level, the learning of the GPT-3 is very similar to how human learns, how kids learn. So in the first stage, we give the kids a large number of these books to read. Right? And in the second stage, then we give them a lot of exercise, question, answer. Now, after combining these 2 stages, then the kids will actually learn complex tasks. And they can also generalize to unseen tasks. So researchers actually observed. So why do we need large models, larger and larger models? Right? Observe when a number of parameters reach a certain threshold, then the capability of the model undergo a transformation, sharp change. Right? So this phenomenon, also known as emergent ability or behavior, signifies that the model begins to exhibit abilities that were not explicitly programmed or trained for, transcending the initial design objectives. That was not even part of the training objective. Right? So as the model scales, it starts to grasp more nuanced context, engage in multifaceted reasoning, and even display creative problem-solving skills. For instance, it might start to generate coherent narratives with richer detail, understand and respond to complex emotional cues, or perform tasks in domain it was not trained on, such as basic coding or mathematical reasons. So this transition underscores the potential for a model to unlock unforeseen this level of intelligence and versatility, even when scaled to a large size. And this also challenges conventional notion of what AI can accomplish, and pointing towards new frontiers in general artificial intelligence. So ChatGPT is a versatile talent, having passed Google's engineering interview, as well as the US medical licensing examination and the bar exam for law. So its ability to pass such rigorous assessments highlights a profound understanding of technical jargon, legal framework, medical knowledge, alongside critical thinking and analytical skills akin to professionals in in these fields, multiple fields domains. Also, ChatGPT success in these exams employ a remarkable capability for synthesizing and applying complex information rapidly and accurately. This versatility opens the door to numerous applications, from enhancing educational tools, personalized learning platforms, to revolutionary industries like healthcare, law, engineering. Its performance also sparks a discussion on future of work, where AI entities like ChatGPT could work with humans, augmenting decision-making process, assisting in research, or even participating in creative endeavors. However, this also raises these ethical concerns we need to pay attention to regarding the impact on professional roles, the necessity for continuous skill upgrading for human workers, and the importance of ensuring fairness and transparency in AI's integration into society. Large models have 5 these stages, including this natural language to multimodal learning, logical listening, tool utilization, we call agents, and embodied AI. In the first stage, natural language understanding, this foundational stage focuses on teaching AI models to comprehend and interpret human language. Then, in the multimodal understanding, building on a natural language understanding, multimodal learning integrates visual, auditory, and other sensory inputs with the language processing. Then in the third stage, logical listening, this stage involves equipping language model with ability to perform complex reasoning, solve problems, and draw conclusions based on provided information or data. In tool utilization, or called agents, at this stage, language models evolve into agents capable of interacting with and controlling other softwares or tools to execute tasks. So this might involve, for example, using APIs, databases, or even operating systems to retrieve information, automate workflows, or perform actions in response to user commands. And the last one, embodied AI, this involves integrating language model with physical robots or interactive actors, allowing them to navigate, interact with the real world. And these systems combine perception, motor skills, and the language understanding to carry out tasks in a physical environment. So here each stage embark a significant leap towards AI's ability to understand, interact with, and influence the world. So there's a vast amount of text data on the internet, right? So contain rich human knowledge. So large language models learn from this extensive textual data, compressing and expressing human knowledge. However, natural language only captures a portion of human knowledge. So humans, as we all know, perceive, understand, and interact with the physical world through multimodal information, such as text, image, video, audio. So how to fully explore and utilize these heterogeneous yet inherently interconnected data is the key to advancing towards more general and intelligent AI systems. So multimodal large models have made a significant stride in recent years, encompassing a series of these novel models, as shown on the right side, including GPT for vision, Gemini from Google, and also Qianwen Vision. Here, GPT-4V is a multimodal model released by OpenAI. Here, V stands for vision, enabling ChatGPT to understand images beyond the text, showcase its strong understanding and the listening capabilities for visual context. For example, understanding and reasoning of complex natural images, comprehension of various tables, charts, or documents, for example, in a research paper, and mathematical scientific computation and intersection. Gemini is another popular one, multimodal model. It was released in December 2023 by Google. And just in a few months, it released a 1.5 version with enhanced performance and a breakthrough long context window of 1 million tokens. So Gemini models are built from the ground up for multimodality and combining and understanding text, images, and audio and video. So these large scale models, language and multimodal models, due to their remarkable generalization capabilities, will bring about a disruptive impact across various industries, including education, scientific research, business assistance, industrial upgrade, public service, etc. And the application of these models in the transportation sector involve utilizing deep learning models with massive parameters to address various challenges and issues in the field through the analysis and learning of transportation data. And these models can be employed for personalized traffic information exchange, travel, route planning, automated, proactive supervision, and autonomous driving. And here I mentioned 3 primary potential application scenarios, including transportation, mobility, assistant, intelligent traffic monitoring and management, and smart traffic dispatch and planning. And here I show 3 application examples across these scenarios. So as a mobility assistant, the large-scale traffic model serves as an informative aid, enabling users to enhance their road safety awareness. For example, it can facilitate queries on traffic regulations, such as inquiries about penalties for drunk driving. And beyond this, it offers personalized route planning, optimizing journey routes for users based on real-time traffic conditions. While in the intelligent traffic flow prediction, the system is capable of intelligently forecasting congestion conditions. And by leveraging its predict capabilities, it dynamically adjusts route recommendations to avoid anticipate traffic jams. And with the smarter traffic monitoring and management, the technology enables real-time detection of anomalies on roads, such as traffic accidents, and respond to these events. Furthermore, it employs digital twin technology, creating a 3-dimensional perception of monitored areas that mirrors the real-world environment. And this digital representation facilitates swift incident assessment, management, decision-making, and even simulates alternative traffic routing strategies to mitigate congestion caused by incidents. So next, I will go through a few applications and how AI can make impact in transportation. First one is a visual. It's a pure vision foundation model for transportation. And here, focus on traffic management. So traffic management has transitioned from traditional manual pictures combined with video analysis for the area of these digital twins, as we just mentioned last slide. However, fine-grained management based on digital twins still face many technical challenges, such as how to efficiently utilize massive amount of visual data, how to ensure the accuracy of this 3-dimensional information perception under different weather condition, traffic condition, and visibility conditions. Now, we have developed a visual foundation model based on transformer architecture with 1 billion parameters for traffic perception and to address various issues in traffic road testing perception. So the model will simultaneously process all visual data from all views, all conditions, and high precision road network map information within a region, then directly output 3-dimensional information, motion information, and predicted trajectory for all traffic participants in that region. And it outperforms traditional approach in terms of accuracy, stability, and generalization. And here is the detailed model architecture model architecture. I will not get into detail. So our model will first simultaneously process all visual data. And then the model's processing of data are 3 modules, including image encoder, radar encoder, and scene visualizations. And finally, subsequently, the model aggregates these features from different times, different perspectives, and sensors into a unified scene BEV space through a BEV encoder module. And then finally, these combined BEV features, a task-specific decoder module will be introduced to decode various 3-dimensional information about the traffic targets of interest in the scene. And our visual foundation model designed to excel in intricate environments and has been deployed along the Chengdu-Lun Expressway and renowned as China's most heavily trafficked highways. And this deployment signifies a major milestone, overcoming the intricate perception obstacles inherent to such densely populated and dynamically changing road conditions. And by enhancing real-time analysis of traffic flows and vehicle behavior, our technology is ensuring heightened safety standards and optimized traffic management, and demonstrating the potential of these large-scale visual foundation models to transform urban mobility in densely populated cities worldwide. So the recognition and understanding of traffic incidents, particularly traffic accidents, is a topic of paramount importance in the field of intelligent transportation systems and intelligent vehicles. And identifying and comprehending complex traffic events is highly challenging due to the intricate nature of traffic environments, diverse observational perspectives, and the multifaceted causes of accidents. And the advent of large-scale multimodal models such as GPT-4 has introduced an innovative approach to addressing these issues. Traffic accidents are mostly the most deadly factor affecting the safety of urban travelers for citizens, and the real-time detection and the timely handling of accidents through urban video play a crucial role in preventing secondary traffic accidents and alleviating road congestion. However, the diversity of accident types and the complexity of the road scenarios make it extremely difficult, leading to a large number of false alarms and traffic, such as waiting for red lights, traffic congestion, and temporary parking. So next, we first explore the possibility and the potential of these multimodal models for understanding these complex traffic situations. So first case is dawdling, which is a common type of traffic accident, usually occurring in areas with dense traffic, such as urban settings. And the sequence of image are shown on the left side. Now we can observe that large multimodal models can correctly recognize the car accident shown in these images and accurately identify it as a dawdling. So this actually indicates that these models align the text semantic feature of dawdling accidents with semantic context captured in multiple images. It can also provide an overall accurate description of the accident. And this example demonstrates the feasibility of generating accident reports based on key frames and provide a good example of vision-based traffic report generations. Now on the right side, based on the precise understanding and the description of accidents, we delve into the model's high-level reasoning and inductive capabilities. So by querying the causes of accidents, we assess its causal influence ability within a given scenario. So the answer show it can include specific accident contexts, such as here show wet road surface to provide possible reasons for the accident. And additionally, these models also attribute the primary responsibility of the accident to the act of opening the door, which is consistent with the common traffic regulations. A second case here I show here is they call collision between car and two-wheel vehicles, which are also common traffic accidents. We can see that the model can recognize the X type as car struck the motorcycle based on the provided key frames shown on the left side. And the generated accident reports also accurately describe the initial scene of the accident, the process of the collision, and the aftermath, as well as the final consequences. So this example shows the tremendous potential of these large vision language, large multimodal models. However, they still face challenges in complex scenarios. So here, this slide, left side, this slide shows a case where the model fails to recognize either the accident or notable traffic events within these frames. So although it's obvious for human beings to identify the abnormalities in the images, the model still describes it as having no evidence, right, of an accident or unusual event. Interestingly, on the right side, so the model can successfully recognize the accident after plumping highlighted visual cues on the involved yellow car in the images. And it can also describe the accident process relatively accurately in this time. So this shows if we can combine these large models with traditional small models. These small models will recognize small objects, and combining these two can potentially make the model much more accurate and reliable. Here show a second failure case is called jaywalking, which is a typical common example of traffic rule violation, usually referred to as an act of pedestrians crossing roads where there are no crosswalks or traffic signals. And the model here in this case fails to recognize two pedestrians crossing the road, but only recognize one of them and viewed the other one as actually viewed back. And in this case, the model can still reason that this traffic violation behavior is jaywalking based on the traffic environment in the images, right? And based on the context that the one recognized pedestrian crossing the road there. And here's a summary of the main results of all the courses evaluated actually across several major capabilities of interest. So in summary, these large models have made a significant breakthroughs in understanding this video context through textual descriptions, which provides the possibility of accurately detecting accident segments in real-time videos through textual description of traffic accidents, which is beyond purely the vision features. However, directly applying these general large multimodal models to the analysis of traffic accidents still face major challenges. So on one hand, there's a severe deficiency of urban traffic video text data, making it difficult to train large models for city videos. On the other hand, large vision language models still tend to get confused when understanding specific vehicle behavior in a traffic scenario. And moreover, large-scale models, as we all know, also present has the issue of hallucination issues, where they may falsely identify unclear areas, such as accident targets, and leading to false reports of accidents. The first failure case already gives us a clue how we can improve large multi-models in this case. So to address issues, including including lack of video text data, insufficient understanding of the dynamic vehicle behavior, and hallucination issues. And we have proposed 3 technical solutions to tackle these challenges. First one is the urban image text data augmentation. So basically, by using a small number of traffickers seeing accident videos and the paired accident text as seed data, we propose to align a large number of unlabeled these videos from urban scenes with textual description from urban traffic accident reports. And this will expand the number of these pairs, image text pairs for the training. And then through the disentangling of image visual context information and the video motion information, along with the enhanced learning of the motion text alignment, the urban image text model is transferred to urban image text to video, text video large models. So from transcend from a large image model to language video models. And finally, by utilizing traditional, as I already mentioned, traditional is a small model, small vision models to detect, tracking these objects, then using this information as a prompt for the large multimodal models. And we can mitigate the issue of hallucination. Right? And this method dramatically reduce the false alarms of accidents. So through these technologies and this deep integration of these technologies, we can develop a citywide video text large models that deeply understand vehicle traffic behavior and with minimal hallucinations. This model can then placed at the final stage of entire urban video real-time analysis pipeline for the final judgment of accidents. And this pipeline can increase the accuracy of the pipeline from around 30% in the past to around 70 to 80%, achieving a dramatic enhancement of the model. And the proposed pipeline allows for automated real-time detection and the reporting of accidents. And the final application I want to talk about is large language models for building a transportation agent. A hot topic since last November is this what is called AI agents. With their rapidly advancing capabilities and integration into various aspects of society, AI agents are poised to redefine the way we live, work, and interact with the world around us, and their potential to enhance efficiency and problem solving span across industries. So Bill Gates forecasts the paradigm shift in computing as we know it, with AI poised to redefine user experience fundamentally. So according to Gates, AI's integration into our digital ecosystems will soon transform the way individuals interact with technology, making computers more intuitive, proactive, and personalized than ever before. So some application of AI agents Gates mentioned in his blog includes healthcare, education, productivity, and entertainment, shopping. And I believe it will also make a big impact in the area of transportation in the future. I think one area that AI agent can make a significant impact is transportation management. So here show the transportation management system employed by road safety supervision team and has several key functionalities, including here comprehensive equipment management, traffic incident management, work order management, as well as traffic situation awareness and prediction. These traditional systems, they have certain limitation or constraints. First, the operation efficiency is low due to the reliance on drop-down manual interactions. That's how human will interact with these systems. The second, adjustment to existing functionality and development of new features require re-customization and consuming significant research and resources. These problems can be alleviated by integrating a large language model agent technology. An AI agent that incorporate large language models at its core serve as the central nervous system, not just the brain, but also the memory, planner, and tool set for managing and optimizing transportation systems. So let's delve deeper into this how this configuration operates within a transportation management context. First one is the brain. In the middle, the agent. So the brain acts as a cognitive powerhouse, processing and interpreting vast amount of data from diverse sources. The memory, including short-term, long-term memory, retains historical data, learns from past events, and recognize patterns. Then we have planning. They utilize the large language model's capacity for complex reasoning. The agent formulates both long-term strategies and immediate tactical plans. So the planner will make decisions based on the context. Learn the tools. Then based on planning, the agent interface with various subsystems and tools, functioning as a command center for automating numerous processes. So here I show a very simple example, simple demo at how we can use AI agent to query a transportation database. Because in the area of traffic, we have a huge amount of traffic data in the database. And in this case, the demo shows how we can use agent to interact with the system using plain language. So here the query is, please count the number of events happened daily between January 1st and January 31st in 2023. And in this case, the agent will retrieve the number of events from a traffic instance table for different dates and present this information using a line chat. And behind this simple interaction, the AI agent will understand the query. So in this case, it will utilize the natural language processing to comprehend the user's request, extracting the details. Then it will access the database, connect to the transportation database. Then it will retrieve information, right? So queries database based on the extract information, fetching the request information. Then finally communicates the results. So present the information in a clear, user-friendly manner. So this is a very simple example, but building upon this foundation, more complex systems we can build by incorporating additional features and functionalities. So this will fundamentally change the way we interact with the systems, with database. Actually, here is a recent work from the transportation field. It's called Traffic Performance GPT. So actually, this paper appeared just 1 or 2 weeks ago. Right? And this week proposed an intelligent online chatbot they call GPT for efficient, customized transportation management, empowered by a large real-time traffic database. So this framework will leverage contextual and generative intelligence of language models, ChatGPT, to generate accurate SQL queries and natural language interpretation by employing transportation specialized prompts. And this work, similar to us, demonstrates the potential of AI agents in traffic management and analysis. So finally, I will introduce a few recent advancements in the field of AI. As many of you are aware, Solar marks a significant milestone in the evolution of AI, as it transcends traditional boundaries between text-based inputs and visual outputs. By translating written narratives into vivid cinematic experiences, Solar ushered in a new area of creative possibilities, empowering content creators, filmmakers, and advertisers like to conceptualize and produce high-quality video context much faster and more dynamically than ever before. So this technology hints at the future of personalized and interactive media, where customized videos could be generated on demand based on individual user preference or real-time data. And this has profound implications for fields such as news reporting, e-learning, and gaming, where adaptable, immersive content can significantly enhance audience engagement. As the technology behind solar continue to evolve and refine, we can expect an explosion of these context, innovative context formats, and various applications. And I think one potential application in transportation is generating comprehensive corner cases, for example, scenarios for training these autonomous driving perception models. The second one is this robotics. At the GTC 2024, a few months ago conference, NVIDIA launched a project called Keynote. It's a foundation model for multimodal computers. So this project signifies a monumental leap in robotics technology, harnessing the power of advanced AI to enable robots to perceive their environment more accurately, understand the complex commands, and make decisions akin to human reasoning. And this will make full use of recent advancements in AI, including its language, vision, and etc. By integrating these foundation models, robots can now interpret visual cues, auditory signals, and even emotional subtleties, fostering a new level of human-robot interaction that is intuitive and responsive. And one potential application is a various type of robots we use in transportation. For example, is the maintenance inspection robots. And finally, this last slide illustrates this diverse spectrum of AI applications within transportation. As I already mentioned, these 5 stages, encompassing areas such as mobility assistance in stage 1, traffic analysis, stage 2, transportation scheduling, planning, stage 3, and AI agents in stage 4, and autonomous vehicles and others in stage 5. And here just show a few examples. As we have seen in recent months or years, the progression of technology in the AI field is rapid, and we anticipate AI's influence on transportation to grow exponentially in the years to come. As AI algorithms improve, data processing capabilities amplify, and the novel sensor technology integrates, future transportation networks will become increasingly smarter, more efficient, and safer. AI is poised not only to refine existing systems, but also to facilitate the emergence of new service models and transportation solutions. And looking ahead, we envision a transportation ecosystem that is safer, greener, and more efficient, with AI playing a more and more important role. Thank you.
Jieping, thank you so much for your insightful presentation. Your overview on the large language model and also the foundational model, it's very interesting to me, and your application on the mobility assistant, the video monitoring, and also the instant management. It's very important to the transportation field. And so I think due to the time, we will not have time for Q&As because we are 15 minutes late to the next session. So I will cut off a little bit in terms of our a break time, and let's take a 5-minute break, and then we'll start our first panel. Thank you.